Okay, yeah. So I'm recording the session, so I will upload the today's internet class video together. Okay, so in general, from our last time discussion, we were talking about the robot modeling. How do we represent the robot in the kinematics and in the dynamics model using a mathematical approach? So the first topic about the kinematics is, in general, we said this kinematics will allow us to program the robot or to control the robot motion either by having the joint state or joint space, or we can say that it is from the operational space. So what is the difference? The operational space means we have a tool center point as a starting point, but in the joint space we have theta 1, theta 2, theta 3, theta 4, just which are the joint variables up to theta n, where n is the number of joints. Where the TCP is only the representation of the tool center point, which is x, y, z in the Cartesian coordinate with angles like rotation about x, rotation about y, and the rotation about z. So here we have vector with 6 parameters: position x, position y, position z, rotation about x, rotation about y, rotation about z. And in the joint space, we have the joint variables, which are the angles of all the joint parameters from model 1, model 2, model 3, 4, and then model n, depending on the number of degree of freedom. So if you have n degree of freedom, then you have n variables, n joint variables, so joint space variables. That's what we have been discussing last week. So this is from the kinematics perspective. Yeah, so actually the one point is, when you talk about the joint space or the operational space, we can discuss with respect to the kinematics forward or inverse. We could have forward kinematics in general, which is a multiplication of each matrix. For example, n from 0 is a 0 1, a 1 2, a 2 3 dot dot dot, then a n minus 1. So this is a multiplication of the kinematic chain. This is a series, or this if it is a continuous, it's a series, so you could make like something like this. The other is the inverse kinematics. This forward kinematics uses the joint space in order to compute the tool center position, whereas the inverse kinematics use the operational space variable as an input and then calculate the value of theta 2, theta 3, something. So up to theta n. As we have said last time, there are so many approaches for inverse kinematics, because we said that if we want to make the inverse kinematics, then we will have some challenge regarding the computational solution. So maybe sometimes it is not easy to find the analytical solution. So this time maybe you could be interested to check if it is possible with the numerical solution, or maybe by learning techniques. Maybe you can use neural networks, or maybe some artificial intelligence techniques to determine the actual position of the robot joint parameters from the tool center point. So that's what we have been talking about. And also we said that sometimes there is a possibility to have a singularity. This singularity configuration is where the robot has no solution, or where the solution is not defined. This leads the robot to some kind of confusion, where the robot will fail to decide the actual position or the config orientation of the robot. So this time we have to think how to avoid such kind of singularities in the space. That's what we have discussed in the kinematic session. Okay, then the other is about the dynamics. In the dynamics, we said, even though there are various approaches, two are the most common. from the dynamics. This common approach is Lagrangian, and the second is this is a Lagrangian approach, and the second is the Newton-Euler approach. So Newton is the linear motion, Euler is the rotational motion. So it is a combination of the linear and the rotational motion. So in general, even though the approach is different. For example, for the Lagrangian, we are using energy-based, but here we are using just a vector representation to compute dynamics of the robot system. So whatever it is, the solution is the same. So at the end, you will have an equation which is either a force or a torque, which has mass times the acceleration, and the Coriolis effect, which has velocity, and also it's a function of position as well. And also, finally, you will have gravitational effect, which is only a function of position. So this will give you the final force or torque model. So just this we can rewrite it as m theta double dot, c theta dot, and g theta maybe something. So here we have mass matrix. Here we have a centrifugal and a centrifugal component, which is called Coriolis effect, or damping coefficient, and so on. In different. And also here we have gravity, which is only due to the height of the object and the mass of the rigid body. Okay. So that's what we have been talking last week. So the Lagrangian approach that we discussed last time was, first you have to construct your Lagrangian variable, which is kinetic energy minus potential energy. This kinetic energy is also a combination of the linear and the rotational components, which is 1/2. Then maybe the linear, the angular velocity, transpose, mass, theta plus 1/2, v transpose, mass, and something like this. This is indirectly, this is just to mean 1/2 of mv square, which is in the particle, or in the particle, with the particle, you can represent like this. But if it is a rigid body with a matrix, this v square means in a matrix, it is something vt plus vt times v. This is how we represent a square in matrix. That's how it is. And the other point is, since we have velocities here, we discussed about the Jacobian representation. So what we said is Jacobian is nothing; it's only a method to map velocity, the linear velocity and the angular velocity together. So you have, for example, v, which is Jacobian times theta dot. That means this is Jacobian, which is independent of time independent. This is a velocity, which is a angular velocity, which is time dependent, and this is a velocity, a linear velocity, which is time dependent as well. So Jacobian is a time independent is a time independent parameter which map the angular velocity with the linear velocity. That's and actually on this point we started to discuss different approaches actually for a Jacobian. For example, if you have Tuli center point position as L1 cos theta 1, L1 sin theta 1, and 0, 1, this is only the position, okay? Position of the joint with respect to 0. If you have something like this, then Jacobian means this. If you want to calculate the velocity of one means Jacobian of theta 1 dot. So derivate this one. If you derivate this one in time function, then it becomes v1 equals to L1 minus L1 sine theta 1, L1 cos theta 1, then 0, 0. Then we said this is then times theta dot. Then we said this is a Jacobian. We said this is a Jacobian. And this Jacobian has no time function. You know, it is not time dependent. It's not time dependent, independent of time. And the advantage is, you know, it will allow us to map theta 1 to v1. That means if you want theta 1 dot, you know, you can simply inverse. If you say this is Jacobian, then it is Jacobian inverse v1. Could you see now? I can easily compute my joint variable velocity by only inverting, by multiplying with the inverse of the Jacobian. So that is the advantage. That's why we want to use the Jacobian. So this Jacobian can be Jacobian of the prismatic, which is due to translation, and the Jacobian of rotation, which is due to the revolute joint. So due to the revolute joint, G0 and the GP for prismatic joint. If you have only a rotational motion, then this is 0. If you have only a translational motion, this is 0, but this will remain. That's what we say in Jacobian. And then if you see on the slide, actually just around the last page, you see some procedure where I described the relationship of the Lagrangian, yeah, and the Newton-Euler, which tells you finally they will have the same equation, but instead of, you know, now if you have a generalized force, which is mq double dot plus cq dot plus gq, you know, q is joint variable. Just don't worry, if I use theta or q, I mean the same thing. Okay, so now if you use the Lagrangian is L minus du, then dl over dt, del L over del q. It's a partial derivative. Maybe I prefer to use a small letter, minus del L over del q equals to the generalized force. This one, right? So we said this dl over dt, del L over del q, the partial derivative of each del L over del q is equals to m q dot plus cq dot plus gq, where, you know, where this is a combination of mass plus inertia. It is a matrix, okay? It's a matrix which comprises the mass and inertia. And we said this is Coriolis. And this, we said this is gravitational load. Okay, so now to simplify this one further, you know, still because it is a mass, it is inertia, so it's better to use the Jacobian approach, and the Jacobian equations were given in the slide, so you can refer that, and then also maybe if you want to go in detail, you can read the robotics books. That's the point, and yeah, so actually this course is not aimed to go in depth actually, because robotics is very wide and it's very vast, and we are not supposed to go in detail actually, but you have to understand the basic highlights, and you have to able to justify, and also you have to able to argue which method you could use for different scenarios. For example, if you are given some use case, industrial use case, or industrial automation use case, then you should argue one method over the other. For example, if you are asked about the difference in the similarities between the Newton-Euler and the Lagrangian approach, you should be able to distinguish what is Newton-Euler and what is Lagrangian, what is the advantage, what is the disadvantage, from the computational complexity, from the representation, from the efficiency, and so on. And also, you have to argue the difference between the dynamic modeling and the kinematic modeling. What is the benefit of kinematic modeling and what is the dynamic modeling used for? For example, if I ask you to design a robot system, a robot system or a robot cell for collaborative assembly task where the human and the robots should work in the shared working space, then kinematics alone is not sufficient because the robot should be able to feel the force applied from the human operator. So the question is, how do you incorporate this information into the robot model? This time, I would like you to discuss the dynamic model, which takes into account the external forces. And also, this dynamic model also works, if you have a complex task where the forces, from the friction or from the workspace or from the working, or maybe from the workpiece, if all this could induce some fluctuating loads or variable loads to the robot, then this is also a problem. So you have to justify this one as well. And maybe in some situations where you have industrial robots, where you don't care about the dynamics, for example, some of the robots with high payload are really not that. Maybe they don't need to design some kind of dynamics because they are rigid enough. Then they are in a cage, so they are restricted. So a human doesn't access them during the operation and so on. So this time, maybe the kinematics alone is enough. That's all, something like this. And also then maybe you have to argue also, depending on the task, how to sense and how to actuate as well. Because if you are wanting to have a dynamic load, then you need a force sensor which will able to sense the magnitude of force applied from the external body and then make some compensation. So this time also you have to have some concept how to sense the force being applied from the object. Are you going to sense it at the joint or inside the motor, or do you want to make additional sensors on the skin of the robot, which will able to sense wherever the external force is applied and so on? So these things have to be, you have to be able to demonstrate all these things. That's all about the robotics session. So this aim for automation. It's not only a robot. It's not only a robot that is involved in the automation. There's also other machine tools like CNC machines or numerically controlled machines or computer numerical controlled machines. These machines are also using the same kind of the same concepts for controlling their motion and for generating their motion. Even though we don't have a serious kinematic change in machine tools, we expect rotational and translational motions at the same time. So if we have a translational and a linear, a translational and rotational motion in the numerical control machine, then the question is, how do we discuss or how do we include in our actually right now I'm not writing this, I'm simply talking. If you are looking at the screen is only white right now. Okay, just So my point is, if yeah, so okay, no problem. Now my point is, how do we extend the concepts that we have seen in the robotics into M.Sc machines? So the point is, we have automation. In the automation, you are supposed to have robots doing some tasks. And also, you know, there are some limitations. You know, robots cannot do all tasks of automation because of the problem with the rigidity, the stiffness. You know, robot is not stiff enough because you have a chain of motors, motor 1 here, motor 2 here. You see now the load of motor 1, the load of motor 1 is also applied on the motor 2. The link is also applied on motor 2, and then again also all of them are being applied on motor 1. Then all of them are being applied on the base, right? It is because of the chain. It is a chain. It is a chain, you know. So due to this, you know, robots are problem with the stiffness. They are not really stiff enough. The second one is, you know, they don't exert, for example, maximum. They don't have high payloads. You know, maximum forces or torque being applied by a robot is limited, or torque is limited. You know, they have a limited maximum force and torque. So this is again a problem. The other is they are not really fast enough. You know, the speed is really not fast enough. So their speed or their productivity is really limited for large or for mass production. They are really not suitable for mass production, but they are really suitable, or they are good enough for flexibility. They are good enough for flexibility, but not for mass production. Also not for speed, you know, for productivity they are not. Also the maximum torque is also limited, the stiffness is also limited, but they are reprogrammable, they are reconfigurable, they are also agile, you know, you can use it for different tasks today for something, and then maybe if you don't like it, then you can change for another task in the other day. So because of this, you know, in automation, you know, if you remember, maybe we have about production capacity, and we have also variables, product variability. So if you have large production variability, you know, if you have large production variability, then robots are the best. You know, robots are the best if you have high variation of product. So robots are best here. Here robots are best. But if you want mass production or with large production, here I could say CNC machines or M.Sc machines are the best. With low production variability, you know, with a low production variation, you know, but with increased mass production. So you could use M.Sc machines. But if you want large variation, but actually, if you have very large variation, of course, robots are not even good. It is manual, actually. Here I could say manual, and then maybe I could put here robot here in intermediate. You know, here if you have, I will put here manual. Even it's difficult for a robot to. It's not difficult, but if it is very large variation, maybe, for example, consider sheep, or sheep manufacturing. It's a very big, and also there are a lot of variations. So this time, maybe I will prefer manual plus special tools. Manual plus special tools. Also, robots can be applied with some, but in the intermediate actually here, with between M.Sc machines and between the special tools, I would say maybe robots are feasible. Yeah. So with this regard, in this regard, now we can discuss about the properties, about the behaviors of these M.Sc machines. You know. So what is M.Sc? M.Sc is a numerical control. They have motions, either translation, they undergo either a translational motion or a rotational motion or the combination of both. The typical machine tools for this could be, we can consider CNC lathe or milling or drilling. They are mainly for mass production. They are mainly for mass production or for job production. You know, we can use for job production. Yeah, so now the point is, if we say this M.Sc they have motion, the question is, you know, how we control this motion. Okay, how do we control this motion? Maybe it's better if we go back to the slide and then, yeah, have some summary. Yeah, so in general, you know, they are developed, yeah, mainly in 1952, which was from, yeah, which was licensed to Fujitsu in the from IBM. And then these M.Sc machines were, of course, evolving because of the robotics, because of the computer evolution. You know, as we are getting advanced in computer control, you know, the machines are also, yeah, getting advanced and also, yeah, they are being intelligent. Yeah, so here you see the historical development for these machines in particular. In 1960, even in 1797, it looks something like this. In 1906, it looks something like this. Now, just it looks something like this, just more computerized and more intelligent. Yeah, so in M.Sc machine tools, you know, in general, you could have machine tool unit, the power unit, and the CNC unit. The CNC unit has several CPUs, just like a computer, or maybe microprocessors, depending on the tasks required by the machine tools. The basic one, the basic or the standard CNC milling machine, for example, requires 3 axes and the spindle speed to be controlled. For example, this is one of the screen for the M.Sc control. Yeah, for controlling here you have button. For emergency, for any emergency, here we have buttons, and we have codes for speed, for the starting, and for controlling. Here also we have the buttons for programming and so on. Now the question is, you know, today, since we are in the Industry 4.0 revolution, yeah, we expect these machines and the robot systems to be intelligent, yeah, and also to be to have the digital communication between each unit. So you could expect, you know, what we require, what the requirement of the current M.Sc machines. Yeah, it's a little bit advanced than the previous one. So we don't need to discuss all these things about this. We could have, as we said, we could have emergency stop button, shutdown, feed rate, spindle speed, manual jogging, and something. This is more or less similar with the robot. You should be able to jog it by manual, and also you can use the auto mode. Just the point is, the main thing behind this machine is about the motion, how the motion are being handled. The other is the mechanical system, but how do we let the mechanical system being controlled? So that's the main point of this lecture. So in general, in order to avoid, for example, if you see the robot, we have different programming styles. In KUKA, you have a different programming structure, and you have universal robot with a different syntax, and you have ABB robot again with a different, quite different syntax. Even though the homogeneous transformation matrix, the forward kinematics, that's a mathematics behind every robot, but the syntax and the programming style is quite different from one vendor to the other. So that's really a problem. But this problem was not an issue actually in the M.Sc machines. There is a standard, for example, the DIN standard discusses about the coding structure, about the format, and so on for parts programming. This DIN 66025. According to this, actually, it's also endorsed by the ISO standards and the EIA, which is Electronic Industries Association. So this is already endorsed. So now the point is, according to this standards, there are two functions in general. First is we have M function, which we call it a miscellaneous function. And we have a preparatory function, which we represented with G. Others are auxiliary. We could have representations for tool selection. For example, if you have multiple tools inside, you could have designations for speed, maybe with S, and for blocks, and so on. So now what are these miscellaneous? What are these preparatory functions? What are these miscellaneous, and what are the preparatory functions? Miscellaneous function means, for example, if you want to have a coolant on, switch on motor, switch on coolant, switch off the program, something like this. You can order by any function. M03, for example, start the program. M07, something maybe coolant on, or 08 maybe off, just something like this. I'm not sure if the M08 is coolant off, I don't know. But there are such functions. We have this listed later. You will see this listed later. The other is about the G function. In the G, you have preparatory functions. For example, go rapid, move linear, move circular with clockwise, move circular counterclockwise, move spline motion, something like this. Could be possible, so you have this kind of preparatory functions. So now the point is, we don't need to go in detail with all of them, but we would like to see to the main functions which really controls the motion of these automation tools, so that you will be able to choose between robot and the M.Sc machines, as well as you will be able to program the M.Sc machines and so on. So the first approach is, according to the standard of this Electronic Industries Association, the first approach is to select your reference frame, as we did in the robotics. So how do you do the reference frame assignment? So the approach, the standard is, first you will start from the axis, which is always along the direction of spindle. And the second is the X motion, which is normally parallel to the longest dimension of the primary machine tool. And the Y-axis follows the shortest dimension, or which is the right-hand rule. Yeah, you can say directly it's the right-hand rule. For example, here you see in the Cartesian coordinate, for example, if this is a lathe machine which rotates, and the rotation is the rotation here, the rotation of the tool workpiece, rotation of workpiece will allow the material removal. So there's a tool, stationary tool, and this stationary tool will remove the material from the rotating workpiece. Okay, so this time the axis of tool will be the axis of the rotation. Sorry, the axis of rotation, which is axis of rotation is this one. Axis of rotation is Z axis always. Axis of rotation is always Z axis. Then axis of the tool, the tool is moving this way. This is axis of tool, or which is X axis. Here also the tool is moving this way. The tool is moving towards the object, to remove the part. So we assign X axis. The axis of rotation of the tool is we consider as Z axis. If we got the X and the Z, then the third one is right hand rule. So now here you got X axis, then you get Z axis, the third is Y axis. That is Y axis. So you follow the right hand rule. So the right hand rule, for example, if you point your thumb Z axis, then you can point your forefinger to X axis, then upward, the middle finger will point upward. So the right hand rule. So the rotation about Z axis is a rotation of the tool, the rotation of workpiece. Along X, there's a translational motion. This translational motion is called feed. It is called feed. If you have the speed, then it is called feed speed, feed rate. The Y-axis is actually nothing for now. We don't have any job on Y-axis. So yeah, so that's a point here on this. Yeah, now the other point is on this slide, actually on page 14, on this page 14, we have a different job. This is not a turning operation, this is a drilling operation. For this drilling operation, again, we follow the same concepts, but during the drilling, it is a tool which rotates as it's given here. It's not a workpiece, it is a tool that's going to rotate. Whatever it is, the rotation of this tool will be considered as Z-axis. Will be considered as Z-axis, so it is a rotation of the tool. Here it is tool rotates. Tool rotates here. So the rotation of this tool acts as Z-axis. Then the longest axis will be considered as X-axis, and the shortest will be considered as Y-axis. Yeah, because now we have a job. Either we translate along X-axis or translate along Y-axis, but depending on the axis length, we can decide whether we choose X or Y. Yeah, so the same is true here. Here the same is true. And in the second, we have different operations, but we have to choose a reference frame at one point. Maybe here this reference frame. From this reference frame, we have the X component and the Y component, and then with respect to that, whether it is either it could be absolute or incremental, we have motion, just to pause. Now the other question is, sometimes you could have a complex geometry. For example, you could be asked to plan a motion for a turbine blade, for example, or for a turbine blade. If you have turbine blades, maybe let's see if there's something on the internet. Yeah, for example, if we see here, there is a drilling machine here. There is a drilling machine. I don't know if you see it. Yeah, now here we have a drilling machine. This drilling machine is doing, for example, here, just, there is a contour here. There's a path about this. There is a drilling tool here, and it's making a complex. So assume, just you are looking to make this complex contour. It's not only by a lathe machine or by a milling machine. Actually, this could be also possible by the robot. For example, if the robot has to do some surface finishing or painting, about this. If you want to make painting, as we have seen last time, you should make a really complex trajectory. So this time, the question is, how do you assign your reference frame? How do you make the path and so on? How do you generate the path and so on? This has to be addressed. So actually here, if you see on the third, actually on the figure 10, there's a complex surface, and on this complex surface there is a mesh. Someone can do something like this. Come here, then jump over this, and then make something like this. Then make trajectory something like this. You can make some trajectory like this, but creating this trajectory is not as simple as I'm drawing here. It's very just tough. Takes some time. Maybe you need some kind of algorithm which automatically detects the surface geometry, and from the surface you may generate a mesh, and from the mesh you can maybe make some algorithm which extracts the necessary points, and these points could be used as a control points, and through the control points you can make a path planning using different profiles, like maybe trapezoidal velocity profile or triangular velocity profile and so on, or maybe you could use some parabolic blending, But the question is, how do you generate these intermediate points? For example, here from the mesh, you can say 1 point, 2 point, 3 point, 4 point, 5 point, 6 point, 7 point, 8 point, 9 point, 10 point, 11 point, 12 point, 13, 14, 15, 16, 17, 80, 90, 20. Now assume you generated these pointers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Assume you generated all these pointers, but there is a high probability that these points are not surface. For example, with the first option, if I use only linear interpolation, it's if I use a linear interpolation, I will create 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you see, it is not surface. It's not a complex surface. But now, if I use a different algorithm like spline interpolation, maybe I could make it. Maybe I could make it like interpolation. Maybe this is a little bit better. So I think now you understood why we need algorithms. So in this time, so for such complex surface, how do you generate the motion or the motion path, or how do you generate all those control points is a question, and also the efficiency also depends on your computational capability. That's why we have to find ways for generating these paths. So with this concept, actually, now we can continue to the approach in these emissions. So now we can start. So assume you have different points. So the machine has to pass through this point. The machine tool has to pass through this point. Start here, move here, move here, move here. Point 1, point 2, point 3, then point 4. Okay. So between these points, how do you move the machine tool? And also how you plan between these points, your trajectory. That's one of our main interests. So if you remember in the robots, we said for example, the robot tool center will start slowly, then move, and then stop, then start, move fast, and stop, start, move constantly, and then move, So this is velocity profile, this is the time between this 0 to T1, from T1 to T2 to T3. Yeah, this is actually intermittent motion, but you can make it continuous. Start here, move constantly, and then stop here. So the blue is, you start once, progress, and stop. But in between, you have different points. This is the second option. Actually, there could be multiple options. So this is for multi-point interpolation. Now the question is, between 2 points, the first option is you could have a linear motion, which goes to here, linear motion, or you could have a circular motion, which is circular. This is true for robot as well. The robot could move either linear or circular motion. And the third option could be also, there could be also a possibility to move this way. This is spline. Now, and then the other option is the fast motion with the maximum speed. Yeah. So now let's focus only on those 3 motions. Let's focus only on those 3 motions. Now in machine tools, actually this commands, for example, the linear motion can be commanded by G01. G01, you know, can be commanded like this: G01 move X 10 meter, 10 centimeter, 10 millimeter, or something. Y 10, Z 10. For example, this is one command. So this means move from the current position to X10, Y10, and Z10 from the current. Now, if you use G02, it states G02, X10, Y20, radius 5. From X to Y20, from X10, Y20, you know, from the current position, move to the desired point with a radius of 5 along the clockwise direction. The same is true if you use G03, move to the desired position from the current with desired coordinate points. So this is linear motion, circular motion, and then you can extend to the spline motion, you know, with the same concept. Now, even, you know, just having a concept how G01, G02, and or 03, G01 or 02 or 03 works is sufficient for this lecture. Yeah, this also is sufficient. So let us start with G01. So in G01, assume you have XY plane. You want to move from P start to P end. You know, you want to move from PS to PE. This is your fixed reference frame, which we call it a global reference frame. So in between this, I will assume here I have XS and YS. Here I have XE and YE. So the distance between XSE to XE is the distance between to this is delta X, which is XE minus XS. I will say the distance between to this is delta Y, which is Y E minus YS. Okay, then the distance between PS to PE is the linear motion that the machine tool has to move. But between PS and the PE, you know, it is not a single point. The robot motor has to rotate so many times. Maybe you could say you could have some sample points through which the machine has to pass. Okay, so PS 1. Wow, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know, we have 10 points. Between PS and the PE, there are 10 points. So delta X divided by 10 is, we call it delta U along the X, maybe. Delta Y divided by 10 is delta of U about Y. That means it is this, you know, just divide like this. So I think you know this concept actually from your mathematics differentiation, something like that. So delta U1, delta U2, delta U3, and so on. You know, so we call this one resolution of the machine. The accuracy of the machine, you know, it's a resolution. How accurate the machine is defined by this delta U. Maybe if we assume all delta U are constant, delta U along X and along Y are, if they are constant, we assume it is delta U. So in general, and we assume N as number of samples. Okay, so from this concept, I will say X of 1 equals to XS plus delta x. x2 means at this point, okay? x2 means x1 plus delta x. x3 means x2 plus delta x. True or not? Then I could write xn equals to xn minus 1 plus delta x, or xn equals to xs plus n minus 1 delta x. Is it true or wrong? Did you see now what I wrote on the whiteboard? I think yes. Okay. Okay, so just you follow the same technique. Then finally, we will have one equation, which is x1 equals to xn equals to x of starting plus n minus 1 of delta x, and also y of n equals to ys plus n minus 1 delta y. This is the main equation for G01. This is the main equation for G01. So G01 uses this equation to compute the next point. So next point. So what does this mean? This means the machine will start. The machine will start here, move 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 here, and then finally here. That's how the machine can perform the task. So this depends on the motor property. The motor property. What does this motor property? RPM of the motor, the resolution of the motor, and also then the capability of the system as well. Because, for example, if you have a steel workpiece, and if you want to make a depth of cut of, for example, 20 millimeter, then it is difficult, right? So it depends on the job, and then also on the property of the motor. So this is a linear motion. So this is a linear motion. The second point is about the circular motion. So we can assume the same thing. We have x component and y component here. We have starting position and we have end position. Between these, we want to make circular motion, something like this. Okay, so actually we have here 0. Here we have a starting point, and here we have the end point. And here this is the path. So the path is shown with the red color here. So this is circular motion. Okay. Now, if we consider only this circle, and if we consider here as enter point, and if we consider this as a radius of the circle, from the geometry, from your mathematics, from geometry, simple mathematics says you know from mathematics, x equals to r cos theta, and y equals to r sin theta. Actually, we don't need to prove this one. It's pretty standard. So you know here from this point to this, you can have a relationship of each point along x, along y, and along z. So we describe into n points. So this means that you have theta as a dependent. So we make say x1 equals to x of starting plus radius of the circle cos theta of starting point plus delta of theta. Then x2 equals to r cos theta 1 plus delta of theta. x3 equals to r cos theta 2 plus delta of theta. This can be finally written as x of n equals to r cos theta of n minus 1 plus delta theta. As we did it earlier, we can rewrite this one as xn equals to r cos theta of starting plus n minus 1 delta theta. N minus 1 delta theta. The same is true. Again, the same is true for the yn. Yn equals to r sin theta s plus n minus 1 delta theta. Okay. So this is a circular equation for G02 or 03. Only the direction matters. Only the direction matters. But behind this concept, actually, there are some assumptions. You know, it doesn't come true for any circles, but we have to take this assumption. This assumption is, so for example, here on this page, we have P1 and there is P2 and there is a radius and there is a center. Now, now this here is the assumption. The assumption is this delta theta, you know, if this delta theta is higher, I can assume you have half circle here. Let's say you have half circle. If in case of half circle, you know, this delta theta is equals to 90 degrees. Not 180 degrees. It's equals to 180 degrees. So for 180 degrees, the chord, the distance between the chord and the arc is equals to this chord length is equals to radius of the circle. Equals to the radius of the circle. This time, so this relationship, this which says this delta theta, maybe it's from your geometry, you know, S equals R theta. That means the arc length is equals to radius times the delta theta. Which so this arc length is equals to this arc length delta S is equals to the radius times this delta theta, which is 180 degrees. So this, in order to be realistic, you know, this delta theta shouldn't be greater than this equation, which is this one. This delta theta it shouldn't be, yeah, maybe it should be around cos inverse. Yeah, this equation should be around this, you know, or shouldn't be more than this equation. If that is the case, then this arc will become a radius, and then it is not realistic. Why? Because what we are interested in is you have points, you know, so you have a point here, you know, so you want to make something like this. So you will have 0.1, 2, 3, 4, 5, 6, 7, 8. So if this delta theta is very small, it's very small, approaching to 0. If this delta is approached to 0, then it means that this length and this length are more or less equal. You know, if you have a radius and if you make something like this, if this delta theta is approached to 0, then you know this delta S also approach to 0. That means this and this is going to overlap. So it is a good quality motion then. Yeah, so it's really important to have this relationship. Yeah, and so finally, this is the equation that you can consider. Maybe you can use this one, or you can use this equation. That's also perfect. Or you can also use this equation. This is also perfect. So on page 75, this is also right, this is also right, this is also right. So you can choose whatever you like. So they give the same result. There is one example here. This exercise we will do it during the tutorial session. Maybe one point that I didn't raise is how to map this one into the velocity profiles. That's what we have to see next week. And yeah, then we will finalize. So in general, what we are discussing today is a basic principle behind every simulation tools. For example, like in the SolidWorks, there is an option to generate a tool path, but SolidWorks is a commercial software and it's very expensive. So maybe it's not suitable for you. So in this situation, maybe you want to make your open source algorithms, maybe in Python or maybe C++. So this time, you know, if you only implement the equation which states the G00 or G01 or G02, you could able to generate your toolpath profiles. These toolpaths can be given to a CNC machine. You can give it to the CNC machine, or you can give it to the robot. You know, that's a flexible, or you can give it to the 3D printing. You know, most of the tasks, you know, the same algorithm applies also to 3D printing. You know, just what we are doing right now is true for a robot, true for CNC machines, also true for the 3D printing. So, yeah, so that's very useful. And yeah, so that's all about it, all about for today for this mathematics. If you have any question or some clarity, actually, I would like to address right now. So let me give you a chance because I was talking a lot. If there are any questions, yes, you can take the mic and talk. One question from Mohammed is about the exam. The question is, when do we discuss about the exam? I think we have been discussing about the exam since the beginning of the lecture. All points that we have been addressing in this lecture are useful, and they can be also used as an input for the exam. So yeah, so I don't think that we need a particular session for that, because for me, I think all what I'm talking is part of the exam.